In this video, we're going to learn another application of our integrals. It's a physics application, and we're going to learn about work today. So first, let's figure out exactly what we mean when we say work. Work has a very specific definition when we're talking about physics. So, if an object moves along a straight line with position function S of t, then the force F on the object in the same direction is given by F equals m times the second derivative of position with respect to time. This right here, you probably know it much more as F equals ma, mass times acceleration. This is Newton's second law of motion. We're just writing it as a second derivative because we already happen to know acceleration is the second derivative of position. But this is still just your mass times acceleration that you've heard before. So if our acceleration, this second derivative here, if that is constant, well, that means that our force is also constant, because mass is constant, acceleration constant would make force constant. So if the acceleration is constant, that means the force is constant. And then we have our work defined as W equals force times our distance. So D is the distance the object moves. All right, well, that doesn't seem too bad. That just says that if our force happens to be constant, well, then I can find my work by just multiplying force by distance, and I'm done. The issue, though, is, of course, what if force is not constant? If your force is not constant, then we're actually going to need calculus to figure out the work. It's not going to be just as simple as multiplying force and distance. So let's talk about what happens if the force is variable. So if our force changes, well, let's let an object move along the x-axis from x equals a to x equals b. And we're going to let a force, F of x, act on the object. And we're going to say that this F of x, this force here, is continuous. So we have some function to represent our force now, not just a constant. It does happen to be a continuous function, but it's a function, it changes. So how do we calculate our work using a variable force like this? Well, this part here is going to start sounding very familiar to us. We're going to divide our interval AB into n subintervals of width delta x. And we're going to pick an xi star in each subinterval. So I think you know where this is going already, because so far all we've done in Calc 2 is we've taken intervals, we've chopped them into n pieces, and we've picked something in each subinterval, then we add up a bunch of stuff and take a limit, and out pops an integral, and then we're done. Same thing here. So we're picking an xi star in each subinterval, and the main point is if we happen to have a lot of these subintervals, so if this n happens to be very, very big, well, then the actual force in each subinterval does not change very much. So if n is very large, then the force in each subinterval doesn't change very much. Why is that? Well, because our force happens to be a continuous function. So we're chopping our continuous function up into little subintervals, and since it's continuous, we know it doesn't have any big jumps in it. So if I pick a small enough little subinterval, the function can't change that much in that interval, because otherwise it wouldn't be continuous anymore. So we're saying that we can estimate the work on each subinterval by Wi is approximately equal to f of xi star times delta x. So what this is here, this f of xi star is a constant. So we're estimating our work using a constant force because we're doing such small little subintervals that we can consider it constant on each little subinterval. So I have my force function with the xi star plugged into it times the distance for that subinterval. So this is our work equals force times distance from before when we said the force would be constant. So we're just estimating using lots of little subintervals where the force is pretty much constant on the subintervals. Well, that's the work for each subinterval. To find the total work, we add all of it up. So our total work is approximately the sum from 1 to n of f of xi star delta x. So we're adding up all of these little works on the subintervals, adding all of that up to get the total work. And now, of course, we can define the actual definition. Our actual total work is the limit of this sum as the number of subintervals approaches infinity. Which we know when we take that limit of that Riemann sum, out pops a definite integral. So this means that my work is equal to the integral of the force function on my interval. Well, that's not too bad. That just means we have to find a force function, and then we have to integrate it. That doesn't sound terrible. Let's do an example. The first example we have is going to be one of the best types of examples in terms of it being not too terrible to calculate. It's a situation where they actually tell you what the force function is. So, an example. When a particle is x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is done moving the particle from x equals 1 2x equals 3. Well, we already found out that our work is supposed to be the integral of the force function over our interval. Do I have the force function? Yes, I do. I have that my force function is this x squared plus 2x. And I have my interval from 1 to 3. So I know that my work, I'm just going to start it down here so it's called the problem statement. Our work will be equal to the integral from 1 to 3 of this force function, x squared plus 2x dx. And then that's all we have to do to calculate the work. So let's just go ahead and do this integral. So if I actually take the antiderivative, I get a 1/3 x to the third plus an x squared, and I need to evaluate that between 1 and 3. So we plug in the 3 and plug in the 1. With subtraction in between, and we get, well, 3 to the third is 27, a third of that is 9, plus another 9, and then this is 1/3 plus 1, and if we add all of that up together, you will get 50 over 3. And the units, well, I personally don't like these particular units. They sound kind of silly, but it's foot-pounds. And that is because we had all of our original units in feet, and we had pounds, and so the units for work, when you have those types of measurements, is foot-pounds. Now, if this were given to us in the metric system, your units for your work would end up being joules. And we will have an example with metric system later on. So imperial system, you're going to have foot-pounds. Metric system, you're going to have joules. All right, so there's our first example of work. And now we're going to do a trickier example for work. It's going to be an example where the force function is not directly given to us. So we have to figure it out on our own. So our next example, we have a 200-pound cable, and this cable is 100 feet long, and it hangs vertically from the top of the building. How much work is required to lift this cable up to the top of the building? All right, so we have a lot of information here, but what we don't have is we don't have a force function. So unlike the last problem, I can't just take an integral of my force function to get the work. I have to figure out what the force function is, and then I have to integrate it. So let's take a look at the important information. I know we have a 200-pound cable. It's 100 feet long. It's hanging from the top of a building. And notice it's hanging. It's not touching the ground. So it's dangling there 100 feet down, and the building's even taller than 100 feet. So I'm going to start by drawing a picture representing this cable in the building, and then we're going to try to figure out this force. So here's my building. And I'm going to have a cable hanging from the top of the building. And I know the cable happens to be 100 feet. So I'm making it convenient for myself. I'm going to place the origin at the top of the building. With the x-axis pointing down. Now, before you start worrying, yes, I know the x-axis normally goes from left to right, but the x-axis and the y-axis, they're just abstract concepts, really. So what I'm doing is I'm using x's because I happen to like integrating with x, and I'm just imagining my x-axis starting up here and pointing downward. Nothing the matter with that, just picture picking up the coordinate grid and moving it around. It's perfectly fine. So I have 0, my origin up at the top. Since the cable's 100 feet, I know down here is 100. And now I'm going to take this and divide my cable. We're going to divide the cable into n subintervals of width delta x. Now, I'm not actually going to draw out all of these subintervals, but I am going to pick one little subinterval here. So this little width here is delta x, and I'm going to pick a particular xi star within that subinterval. So there's my xi star, and I'm picking it in that tiny little subinterval. So, if xi star is in the ith subinterval, then all of the points in that little subinterval are lifted about the same amount. They're all lifted approximately xi star feet. And that's because we're taking this little section of the cable, lifting this little section all the way to the top. That distance is approximately xi star because remember we're choosing really, really tiny subintervals so that the points are so close together they're all pretty much moving the same distance. So if xi star is in that ith subinterval, then all of the points in that subinterval are lifted about xi star feet. And something else that we know about this particular cable is that the cable weighs well, the cable weighs 200 pounds, but that means that it weighs 2 pounds per foot because we have a 200-pound cable and 100 feet of cable. So the cable is about 2 pounds per foot. And so the weight of the ith subinterval of the cable is 2 pounds per foot times however long that little subinterval is. And we know the length of that subinterval is delta x. So this tells us the weight of that particular part. And that tells us that the work on that part is 2 delta x times our xi star. Now, where did that come from? Well, because this weight here is my force, and this guy is my distance. So we used work equals force times distance, that same formula for when you have a constant force. And since we're choosing small enough subintervals, the force is practically constant on all subintervals. So my work for lifting that ith part to the top of the building is our 2 delta x times our distance xi star. So this means my total work, now I don't need my building picture anymore, because now we have what we need. This means my total work is equal to the limit as n goes to infinity of the sum of all of the work on each subinterval. So I have 2 xi star delta x. I just rearranged the order there to put it in the more standard order. And now when I take this limit, we know we get an integral. And the bounds for my integral, we had 0 to 100. That was the length of the cable. And I have my function is 2x dx based off of that sum. Now we just have to calculate the integral. Antiderivative of 2x is x squared. Plug in the 100 and plug in the 0. When we plug in the 100, you get 100 squared, which is 10,000. And our units again are foot-pounds because we were using feet and pounds in the problem. So notice that once this was set up, the calculation was not that bad. The hard part is finding the function for the force, which gives us a expression for the work on each piece so that we can take the limit of that and get an integral. That's the hardest part when they don't give it to you directly. So that was a pretty complicated example. And for those of you that are currently in my class, if you want to see a really complicated example, I'm putting one more on our course page as a PDF. So if you're interested in physics and things, you might want to take a look and see what else we can do with this. If you're not really that interested, you can ignore that PDF, but I just wanted it to be out there for you if you're one of my current students. All right, so to finish this video up, we're going to talk about one more application using work called Hooke's law, which involves springs. So I'm going to tell us what Hooke's law is and then do an example using it. So Hooke's law says that a spring that is stretched x units beyond its natural length pulls back with a force f of x equals k times x, where k is a constant called the spring constant, or sometimes it's called the spring stiffness. So this is just telling us that if you have a spring and it's stretched x units beyond its natural length, so you're actually stretching it, then there's a force pulling back on the spring, trying to bring it back to its natural length. That's always a constant times your x. Now, we can figure out what the constant is in different situations, and then if you want to figure out some work, we would have a force function that we can integrate. Now, before I give us an example using Hooke's law, I do want to point out that the way this is stated, it says the spring is stretched x units beyond its natural length. But this law, the same exact thing, also works for compressing the spring shorter than its natural length. So you can think of that as stretching it negative units beyond its natural length. That sounds a little strange, but just know that this works for stretching or compressing springs, and it works exactly the same way with that spring constant. Let's do an example using Hooke's law. So we have a spring exerts a force of 5 newtons when stretched 1 meter beyond its natural length. We want to find the spring constant K, and we're also going to find how much work is needed to stretch the spring 1.8 meters beyond its natural length. All right, so what are we going to do for this problem? Well, the first thing we need to do is write down Hooke's law. We know that the force is equal to K times X, where X is the distance we're stretching the spring beyond its natural length. I know my force happens to be 5 newtons. When I'm stretching this spring, X equals 1 meter. So I can set up that equation and solve that for my K. Then we'll answer the second part of the question after we find the spring constant. So Hooke's law gives me the force is equal to our spring constant times X. And now I'm going to plug in the information the problem gave us. I know my force is 5 newtons when I stretch 1 meter beyond the natural length. Well, this means, of course, that my K is equal to 5 newtons per meter. That's the first part. That's my spring constant. And now I know what my force is. That constant is a constant, meaning it's always going to be the same no matter how far we're stretching or compressing the spring. So our force for this particular spring is F of X equals that K that we found times X. We have our force is 5X. So now I want to find how long it takes to stretch it 1.8 meters beyond its natural length. Well, we know that work is going to be the integral of our force. I just need to find my bounds of integration. Well, we have to think about what we're doing here. We're taking our spring and we're stretching it 1.8 meters beyond its natural length. So before we stretch it, how stretched is the spring? Well, it's 0 meters beyond its natural length to start, and I'm stretching it 1.8 more meters. So my bounds are from 0 to 1.8. 0 meaning my natural length, it's not stretched at all. 1.8 meaning what I'm trying to find out. What's the work for stretching at 1.8 meters? So now I just have to integrate this and calculate by plugging in my bounds. So my antiderivative of 5x is going to be 5 over 2x squared. And then I just have to plug in the 1.8 and plug in the 0. Well, plugging in the 0 is going to give me 0. So I just have 5 over 2 times 1.8 squared, which if I simplify that, I get 8.1 joules. So this right here is joules. And again, that's just the units used for work when you're using the metric system. I knew I needed joules this time because we were talking about meters and things like that. So I knew it was going to be in joules. All right, so that's Hooke's law. I'm personally a big fan of the Hooke's law problems because they're very straightforward. It's not too hard to figure out the force because you just have to find that spring constant first. But it does check, do you remember that work is the integral of force? So it ends up being a pretty straightforward calculation. These are very good problems for application problems when you don't really know the physics background of your class. I can't assume that everybody has a really strong physics background, but I'm sure some of you do. So I'm a big fan of these problems. I think they're a little easier to understand. The one we just did before this was a little more complicated. And again, there's going to be an even more complicated one on our course site if you are interested in seeing it. But that's about all I have for us today on work. Remember, work is the integral of the force function. When you actually have the force function, it's pretty nice and straightforward to calculate. You just integrate the force function. If you don't have the force function, you have to do a little more work to try to figure out what the force function is before you can integrate it. And then also don't forget that in the cases where we have a constant force, you actually don't need to integrate at all. If you have a constant force, then work is equal to force times distance, and you don't even have to do any calculus. I didn't do any examples like that in this video because, of course, this is a calculus course, so I wanted to make sure I did the calculus examples. If you have any questions, feel free to drop them below. If you're a current student, you can also email or ask in office hours, and I will see you guys next time.